In section 9.3, we're going to take a look at absolute value equations and inequalities. Before we actually look at those types of inequalities, let's actually begin by definition of the absolute value. Everything in this section involves absolute values, so we're going to take a look at our definition of absolute value. Now, if you recall, absolute value is defined. We knew about absolute values back in elementary algebra, algebra 1, but as a reminder, the absolute value of a number is simply the distance of that number away from 0, correct? So for example, if I have absolute value of 5, that means 5 units away from 0. And of course, let's say here's the number line, here there's 0, and this is 5. So that would be, let's say, the distance from here to here. That's going to be absolute value of 5. So we're going to say 5. If I look at the negative side, negative 5 to the left of 0, well, that distance away from 0, ignoring direction, is also 5 units. So absolute value of negative 5 is also 5. Therefore, when we talk about absolute values, we don't really care about direction, whether it's right or left. In either case, both distances are within 5 units of 0. Okay, so that's just the basic of absolute value. Now here we're going to formally define it, the absolute value of a number x. So the notation for absolute value, remember the two vertical lines, right? There you go. That's the notation for absolute value, and that's what you see here. Now, absolute value of any variable x is going to be itself x if x is positive. Because remember, the answer has to always be positive, right? So if absolute value of, for example, 7, the number 7 is already positive, the answer is 7. But if I'm doing absolute value of negative 7, the number I'm thinking now is negative 7. I cannot just write that same number. The answer is not going to be positive. So in order to force this into a positive number, I need to put a negative in front of it, and that forces it to be positive 7. And that's what this part does. That's why there's a need for negative in front of the x. Okay, provided the number x is negative. Okay, now, so that's just definition of absolute value of x. Now here we're going to have a series of statements. Okay, these principles, the top 3, the first 3, the ABCs, these are equations that involve absolute values, and the bottom ABC, the bottom 3, these 3 involve absolute value equations and inequality. In this case, here's the equation, and these are the inequalities. So we got a couple of them for inequalities, and then we got one here which seems like it repeats. It looks just like that one, doesn't it? One that repeats. Okay, and then there's another form of absolute value equality, which we'll take a look at in a few minutes also, and I'll show you that one as well. Okay, let me actually show you this other absolute value equation, and it's this one right in here. Now notice here we have two absolute values, right? I have one on either side of the equal sign. There's one here, one here. Now in this section, in order to be able to work the problems correctly, we need to rewrite all of these statements, whether they're equations or absolute value inequalities. We need to rewrite them without the absolute value symbol. So the key is in being able to translate the statements without the absolute value. Okay, so let's begin with this one. In part A here, we have absolute value of x equal to p. Here we're told that p is a positive number right here. any positive number p. Okay, so that's what p is, a positive number. So absolute value of x equals p, then we are allowed to rewrite the statement in this form. That would be the translation of the absolute value. Notice when we translate it, we're going to lose the absolute value symbol. So that's what this is. Therefore, absolute value of x equal p, where p is a positive number, it's going to be x equal negative p or positive p. And we go through numerous examples. I will clarify these for you. Absolute value of x equals 0, of course, then x must be 0. That's what that says. Now, if absolute value of x equals negative p, in other words, this is now negative p, so this is going to be negative, right? If p, remember, p was defined to be a positive number, so negative of a positive number is negative. So in other words, if I have something like absolute value of x equal negative 4, well, that's impossible. By definition of absolute value, remember, the answer has to be positive. This one has no solution. Okay, so that's what part C is telling us. Now, when it comes to, let's see. I'm trying to see what's the difference between these two. Right in here. Those two seem to be the same. Or those numbers that satisfy. Yeah, they look to be exactly the same. So we already discussed that one. We don't need to rediscuss it. Let's take a look at part B of this statement down here. Now both of these involve inequalities. You see that one? So if we have absolute value of x less than p, then this would be the translation of it. Okay. In part C, if absolute value of x greater than p, this is the translation of it. So again, the key is to be able to translate these statements without the absolute value symbol. Okay. And of course they have the graph. So this would be the solution to that, the graphical solution. This is the answer and this is the graphical solution. That's what those are. Again, we will be doing these as we go through the exercises here. And finally, if we have absolute value on the left equal absolute value on the right side, then x must be equal to y or x must be equal to negative y. Okay, so that's what we're doing in this section. Now let me try to go through and make up examples here, and we'll take a look at these. Okay, so let's begin with exercise number 16 in your textbook. So in number 16, I have absolute value of x is equal to 5. Now remember, what's inside of the absolute value could be positive or negative, because we don't care about the direction. And in fact, I just did it earlier and I erased this one. Absolute value of a number is 5. So what can the number be? Well, if I look at the number line, here's 0. This distance is 5 units away from 0, so is this distance, right? Therefore, the solution is 5 or negative 5. So x is 5, comma, negative 5. There are two solutions in that one. This translates into a disjunction. Now take a look at number 18. Absolute value of x equals negative 8. Now this time, remember, by definition, absolute value is always positive. So it is impossible for it to become negative, isn't it? Therefore, this one has no solution by inspection. Okay. Let's take a look at number 26. In number 26, absolute value of x minus 3 equals 11. Now, whatever is inside of the absolute value, whatever this is, shouldn't that be 11 or negative 11? So the absolute value is going to be 11. So that's going to be the inspiration for our work. Okay, so here's how we're going to do this. We're going to say that this is equivalent to what's in there, that's x minus 3. Could be 11, or what's in there, x minus 3, could be negative of 11, right? And that is what this is saying. Okay, so that's part A. Now, we need to solve these two equations. They're easy to solve. Add 3 to both sides, makes that 14. Or add 3 to both sides of this one, makes negative 8. So we got two solutions to this equation. One is negative 8, the other one is 14. There's a solution set. As long as we know how to translate them, they're pretty easy and straightforward. Let's take a look at, for instance, let's take a look at number 38. Okay, in number 38, I have absolute value of t minus 7 plus 1 equal 4. Before I translate it, I need to isolate the absolute value. So I'm going to subtract 1. So this reads absolute value of t minus 7 is equal to 3. And now we can translate it. This means t minus 7 is 3, or t minus 7 is negative 3. Again, what we're saying is that whatever is in here, there we go, question mark. Whatever is in here should be 3 or negative 3. That's all we're saying by rewriting it on the right side. Okay. Now add 7 to both sides, that makes 10. Add 7 to both sides, it makes 4 here. And we have two solutions to this absolute value equation. Let's look at another type. We're still going to work with absolute value equations. So let's take a look at the case where there are two absolute values, one on either side of the equal sign. So here's the absolute value on the left, and the absolute value on the right side is that. Now, this one, I actually flashed it up here. So which one is this? This is actually the one that we're going to work with. So if you have two absolute values, one on the left, the other on the right side of the equal sign, then this is the equivalent expression we want to write. What we're saying is that either both of them are the same sign. When we say x equal y, it means they both are equal, having the same sign, or one is the opposite of the other one. You see that negative symbol there, the negative sign? So that's what that means. Okay, sorry. Okay, right in here. This is positive, this is negative. So that means they're opposite in sign. So here's what that means. One of them could be, for instance, 4, absolute value. The other one could be negative 4. So those are equal, aren't they? If we ignore the sign, negative sign, they're both 4 units away from 0. Or this could be negative 2. The other one could be opposite. That is true. Now, both of these are included in that condition. Okay. Now, the case where they're exactly the same, I have absolute value of 3 equal absolute value of 3. That's when they're the same and they're both positive, or the same, both negative. And that's what that is. So you can see that the equation that we have here covers all 4 possibilities of what x and y could be as pairs. So let's take a look at this one. We're going to look at the translation of this. So what does this mean? Well, either they're both the same. So that means you simply drop the absolute value. This is when they are equal. They're either both positive equal or both negative equal. Or one of them, let's say the one on the left, is opposite. So I'm going to go negative sign here. Opposite of the other one being x minus 6. It doesn't matter. You could, if you wanted to, put negative on the expression on the left. See, as long as they're opposites, There you go. That's both of these are permissible. But you can see you can get from one to the other, right? Let's say in here, if I multiply both sides by negative, that's what it's going to look like, right? And that is exactly what the equation above is. So as long as you make them opposite, that's all that matters. Okay, now let's work the first one, the one on the left. So here I'm going to subtract x from both sides. When I subtract x from both sides, I get 2x plus 2 is equal negative 6. Then let's subtract 2 from both sides, divide by 2, and we have our first solution. Or, to do the other one, let's first begin by distributing the sign. So I did distributed the negative to both. Then I'm going to add x to both sides. I like having variables on the left side. 4x plus 2 equals 6. A couple of more steps and we're there. Subtract 2 toward isolating x and divide by 4. And from this we get x is 1. So here we have again two working solutions right here. And by the way, there is no need to check the solutions unless like you're not sure if what you did was correct or not. You can always check the solution and see that it works. In fact, just to show you, let me show you something cool. Let me actually check both of these solutions. Okay, so I'm checking this one first, the negative 4. Now, before I plug it in, notice here, in here, they're both having the same sign, right? And here they have opposite signs, right? Because of that negative. So, when I check the solution, I would expect, when I check negative 4, I would expect to get an expression on the left and then an expression on the right that are either both positive or both negative. That's inside the absolute value, okay? I'm not saying like it's going to be a positive equal negative. Inside the absolute value, they're both going to be either positive, or inside the absolute value, they're both going to be negative. So let me plug in a negative 4, and that's going to be 3 times negative 4 plus 2 equal absolute value of negative 4 minus 6. 3 times 4, negative 12 plus 2, and to the right we have negative 10. On the left, negative 10, to the right, negative 10. See, this is what I meant. See, both of these have the same sign, right? Negative, negative. And that is what this is saying. They're either both positive or both negative. So that's covered in there. Now, let's check the one. Absolute value of 3 times 1 plus 2 equal absolute value of 1 minus 6. The one on the right inside, absolute value is negative 5. Look at the one on the left. 3 times 1 is 3 plus 2 is 5. Check this out. You see how these two are opposites? And that's the significance of what we did up here, setting one equal to negative the other one. And so both of them check, actually. And of course this is 5, so is the one on the right. So this is true. The answer is good. With the first check, this is true. So both of those are working solutions. Okay. That was exercise number 48. Now, let's take a look at, so that's all with absolute value equations. Now, let's take a look at something with absolute value inequalities. So, for example, number 58, I have absolute value of x less than 5. And here we want to solve and graph this one. And our answers, we're going to show them using set builder notation and interval notation. Okay. Now, we need to translate this less than 5. So let's go back up here. And this is how you translate less thans. Okay. That's what that is. This is the direct translation. It means what you see down here. Okay. And so let's go back down. Notice on the graph, by the way, on the number line, this is what the graph's going to look like. It looks like a conjunction, right? Remember conjunction we have between two numbers usually, and disjunctions we have two parts of the solution, here or here. So one of these inequalities translates to a conjunction. That's this one, right? This one is a conjunction, and this one is going to be a disjunction. Okay. Now, let's look at this one. So we're looking at all answers. Think about the answers, just guessing them. Can you think of numbers that are less than 5? Well, like 4, 3, 2, 1, 0, right? Of course, they don't have to be integers. It could be pi. Pi is less than 5. But for simplicity, we're just focusing on natural numbers. So we know 0, 1, 2, 3, 4, right up to 5. So 4.99 works. That's on the positive side. But on the negative side, doesn't negative 2 work? Check this out. Is absolute value of negative 2 less than 5? Well, absolute value of negative 2 is 2. 2 is indeed less than 5. So see, negative 2 is also a solution. So if I actually now draw the number line, here's 0. And this is 5, there's negative 5. Less than means everything that's less than 5 means all of the numbers between 0, 5 on the positive and 0, negative 5 on the negative. So this will be the corresponding solution, graphical notation for the solution. Okay. So the translation of this would be between negative 5, x, and 5. So notice from the shaded segment, I can actually write the inequality for that. This shaded segment means everything that's between negative 5 and 5, true? So that's within 5 units of 0. So when you see less than, let's generalize this. If I see the inequality is less than, then we think of this as the word within. So I'm looking at, again, all x's in this example, number 58. I'm looking at all x's that are right here. All x's that are within 5 units. And that would be the translation. Okay. And the set builder notation for the solution is all x such that negative 5 less than x less than 5. See, you just copy this and put it inside the set. That is the set builder notation. We already have the graphical notation is right here. There you go. Parentheses, parentheses, because this is less than, so it doesn't include 5. If that was less than or equal, these would be brackets. So we have set builder. In here we have the set builder notation, and we got the graph. Now let's do the interval notation. I get my interval notations from the graph. It's much easier. From negative 5 to 5, and this is the interval notation. Okay, and there you go. That's a complete example, number 58. Let's take a look at exercise number 63. In number 63, I have absolute value of n plus 2. Again, this time less than or equal 6. Okay, so the fact that it's less than, remember, the word within. So we're looking at all things that are, all things, I mean all things inside absolute value that are within 6 units of 0, right? So this means n within 6 units. So I'm just going to go ahead and write with my inequality. So what's inside absolute value must be within 6 units. And there you go. That's what within 6 unit means. Means between negative 6 and 6. Isolate n by subtracting 2 from all parts. We get negative 8 less than or equal n less than or equal to 4. And this indeed, this is a solution. The set builder notation is pretty simple. All you gotta do with the set builder notation is to put that expression inside a set. There you go. Wasn't that easy? That's our set builder notation. Now next we're going to graph this, right? So here's my number line. And here's 0 between -8, so that's -8, and suppose this is 4. This time we're going to have brackets, right? We're going to have bracket here and bracket here. Right? The reason, because you have equal sign and equal sign. And between -8 and 4, so if I was to kind of like highlight, that would be the solution, wouldn't it? But if you don't have highlighter, you can just as easily shade the segment there. So the interval notation for the solution to this one is going to be bracket -8, comma 4, close bracket. Okay, that's number 63. Now let's see, let's take a look at something that's greater than, such as number 70. In number 70 I have absolute value of 2a plus 5 and then plus 1 is greater than or equal 9. Okay, so first we need to isolate the absolute value, and we can do that by subtracting 1 from both sides. We get 8. Now let me go back. Remember, for greater than, the symbol greater than, that translates, for greater than, this is what we have. It's going to translate into a disjunction, all the ones that are greater than. So here's, oops, sorry, this is going to be greater than right there. So with greater than, we're going to look at, it could be positive, greater than p, and it's greater than p, or it could be less than -p, and in absolute value it's going to be positive, which makes it greater than p. Okay, so that's what those two are. Therefore, let's rewrite this one now. So we can rewrite this as 2a plus 5 is greater than or equal 8. Okay, that means above 8 units. 8 units, if you will, away from 0. Or 2a plus 5 could be less than or equal -8. See that? That means over 8 units on the left side, doesn't it? Let's solve each of these. That's going to be 2a greater or equal to 3. Divided by 2, we get 3/2. Or subtract 5 here, just like a moment ago. That's 2a less than or equal -13. And a less than or equal -13/2. That's what that is. Okay. So now we have it. Let's graph them on the number line. Okay. So let's say here's 0. Greater than 3/2, call this 3/2, 1.5. Greater than or equal to that would be everything to the right of it. For the second inequality, this one, oops, sorry, this one, it's going to be less than -13/2, which is 6.5. So let's call that -13/2. Doesn't have to be exact, but close enough. And this is less than, so that means to the left of it, all the way to -infinity. Okay. Now let's actually, so this is the graphical notation, and now let's actually write this in interval notation. In interval notation, I have -infinity, comma -13/2. Parentheses on -infinity. Because this is a disjunction, we union it with 3/2, comma, infinity. That would be this segment. The other one is this segment. Okay. And there is the answer to exercise number 70. Now, let's take a look at a couple of special cases. Okay, so I'm looking at exercise number 68. In number 68, I have absolute value of 3y minus 4 is greater than -8. Now here, the key is the fact that this is a negative number. Now, remember, by definition, absolute value is always positive, correct? So the answer to this, whatever y is, I don't care. But in there, once we evaluate that expression, the answer is going to be positive with absolute value. And any positive number is bigger than -8, isn't it? So this seems to be always true, regardless of what you choose for y. Therefore, the answer to this is going to be all real numbers for y. The all real numbers is written this way, or in interval notation, -infinity to infinity. And you can try your own numbers in y. Pick anything you like. Try it, and you will see that once you take its absolute value, it's going to be bigger than -8. That's the special case. Now, the other special case, let's take a look at number 77. Okay. In number 77, we have absolute value of 5 minus 4x. This time, less than -6. Again, when there is negative to the right side, when there is negative on the right side, you got to be careful. These are special cases. And make sure the absolute value is isolated and then negative. That becomes a special case. So, now, by the same token, or the same approach as in number 68. Regardless of what you let x be, the answer to absolute value, this is always positive, isn't it? Now, can a positive number be less than a negative number? It can't, right? So this one has no solution. That means the null symbol. And there we have it. So no solution to that. Again, both of these are by inspection. So the special cases are just by inspection. Okay. And with that, we are done with this section. This was all in section 9.3. And that wraps up the section for us.